Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistants, and today we're looking at types of crystals. We're kind of getting more into the nitty-gritty of crystals. And we're asked how many ions are in each unit cell of potassium bromide. Okay? And I have this little drawing here for us to get a little more visual representation of unit cell. And we're going to say that the purple is going to be potassium. So this is our K plus. And red is going to be our bromide ion. Okay? So you can actually just count these up, but it's not going to give you the correct answer. The correct answer has to do with the number in which we can evaluate this based on each of these pieces being a part of a whole, which is to say that just because it looks like there's a whole potassium ion right here doesn't mean there actually is. It's actually just part of a potassium ion. So this does take a little bit of recognizing what the unit cell is representing. So we're going to have to let's look at each species separately. We're going to have our potassium, and we're going to have our bromide. Okay? So for potassium, we have 1 in the center, and looks like we have 12 on the edge. And for bromide, we have 6 on the sides, and it looks like 8 on the corners. So, looking at this, let's think of what a cube looks like. So, when we say that there's 1 in the center, we mean one whole one. So there's going to be a whole atom, a whole potassium atom or ion in the center of this unit cell, because it's not being divided up by the edges of the unit cell. And we know from previous works that each of the corners there are 8 corners total, and each will be occupied by 1/8 of a cell. So this should be an 8. So there should be 8 times 1/8, which is equal to 1. So we have that. We know also that the sides are going to be half of a bromide. So there are 6 sides. Times 1/2, that's 3. So those two added together is going to give us 4. So there should be 4 bromine ions, so bromides. And we have potassium. We know there's 1 at the center. Let's think about the edges for a second. There are 12 edges total, and each of those edges is going to lay somewhere between a side and a corner, right? Because what you're doing is, if you look at kind of what that would look like in terms of the piece itself, it would have this edge here, and it would swoop out on either side. This isn't a very good representation because you're not seeing the dimensional factor. But if you were to pretend like the centerpiece here is just a corner, it's a corner side, it's a sharp angle, you would note that really what's happening, because all the angles are right angles, you would be left with a quarter of an atom. So let's go ahead and change that up. So we've got 12 times 1/4 atom, which would also give us 3 atoms. So 1 and 3 is going to give us 4. So the total number of ions in the unit cell is going to be 4 plus 4, which gives us 8. And that is, in fact, correct for this particular unit cell. This would be face-centered. So you have 8 total ions in it. Let's take a look at another problem that's a little more math heavy, but it also deals with crystals. So we're told that the edge length of this potassium bromide unit cell is 654 picometers. And we're asked what the density of it is. Well, we know the total number of atoms or ions in the cell are, so that helps us in this next problem. So let's start by determining what the mass is. Because once we have the mass, we simply need to find the volume, and then from the two we can calculate density. So mass for this one would be 4 times the mass of the bromine, and then 4 times the mass of potassium. So we're just going to say mass is equal to 4 times 39.10 atomic mass units plus 79.90 atomic mass units. And that's going to give us 476 AMU. And we can relate AMUs into grams by using Avogadro's number. So we got 476 AMU, and there are 6.022 times 10 to the 23rd AMUs in 1 gram, which is going to give us a total of 7.904 times 10 to the minus 22 grams. That is the mass of this unit cell. Then, using our information on that it is a face-centered cell, we can calculate volume, which is going to simply be our edge times, is going to be our edge length, our width of the edge, times to the edit. Simply going to be the width of the edge, or the edge length, cubed. That's going to be our volume. We know that because it's a face-centered cell. So V is equal to A cubed, which is equal to 654 picometers cubed. And we want it in terms, generally speaking, when you're dealing with density, it's usually in grams per cubic centimeter. So for our case, we want to try to get picometers to centimeters. So we might as well go ahead and do that now. So 1 times 10 to the minus 12 meters in 1 picometer. And that whole thing is going to be cubed. And then 1 centimeter per 1 times 10 to the minus 2 meters. And that's going to be cubed. So make sure that if you're going to be relating these, we know the relation between meters and picometers, meters and centimeters, but what we don't readily recognize is the relation between cubic meters and cubic picometers, or cubic centimeters and cubic meters. You can memorize the relation between them, but it's just easier to simply take that relation, cube it, and you'll have the relation between the volumes. So when you do all that out, you come up with 2.797 times 10 to the minus 22 cubic centimeters. And given that we have the volume and we have the mass, we can now calculate the density. So, you recall, density is equal to mass over volume, which is going to be 7.904 times 10 to the minus 22 grams over 2.797 times 10 to the minus 22 cubic centimeters will give us a density of 2.83 grams per cubic centimeter. And that is all there is to it.